understand better. So my name is Anand Koirala, and I'm a postdoc researcher at Central Queensland University, Australia. My research expertise is in machine learning and deep learning computer vision application in precision agriculture. So many of you will maybe in future want to be someone wants to be a software developer or wants to be a machine vision expert in the field, in this field. So what I think is, like, if you browse the internet, you can find so much of the resources in the study materials. I mean, the study materials about what these deep learnings are, what they have been doing. You can find so many publications. So without wasting any time, I think I'll just explain some of the practical examples so you can relate to the practical implementation of these technologies and these methods. And later in the question and answer section, you might, like in the session, you can throw any question. Don't hesitate to throw any questions. I'll try to answer all the questions as much as possible. So to begin with, the title is the Machine Vision and Deep Learning Examples in Agriculture. So I'll present you with some examples. You can look at the slide. So before starting, so as I already said that you one day want to be a program developer or a machine vision software developer, or you can develop some products related to computer vision. So where do you start? You start with the problem, isn't it? So there are some problems in the daily lives that you want to solve. So you have to have a practical approach, a practical thinking on how you start. So I'll try to set up the scene here. So this is an example of a typical farm in Australia where you have the mango trees, and you can see the mango fruits on the trees. It's I think a sunset scene. So you try to put this in your memory. So while I run through all other slides, you have to think, okay, you have to like imagine you are in this situation, and then we try to solve some problems, some related problems using the machine vision methods. So before I begin, so the computer vision is mostly related with the visual spectrum in the electromagnetic spectrum, the visual range. So so that is like the colors of different intensities that you perceive through your eyes and you visualize. So by color, I mean, like, if any object is in a very well illuminated place, there is enough light, you can see those things bright. And if it's somewhere in the corner, around the corner, then that will be like it looks dark, isn't it? It looks dull. So light is a very, very important thing in this machine vision and computer vision. So I'll start with the challenges. So these are the basic challenges for machine vision in the outdoor scene. So if you apply the machine vision software or algorithms in the indoor scene where the lighting doesn't change too much, that's not a problem. You can solve many things. You can find solution. But if you want to apply it in like the agriculture sector, you want to go to the big orchards. Like in the first slide I've shown you, you have to imagine you are in that orchard with hundreds, thousands of the trees. So there will be a lot of variable lighting conditions. There will be overexposure. If you go during the day, and there will be the sun shining on the fruits, overexposed. There will be strong shadows. There will be occlusion from the fruits, occlusion from the leaves, other trees, branches, and so on. And also the size, like the different size, the variable size will actually matter when you do the machine vision, while you train the models and while you do the detection things. So here is an example picture. You can see on the image on the left, you can see the fruits on the sun and on the shadow. on the right side, on the right image, you can see there is a like in a sun. So when there is a sun, like I would say, like you said, I know the machine learning stuff. I know how to do the image processing. I can do a lot of pre-processing. And then what happens, you just went out in this situation to collect the data, taking your camera, and then the sun is directly on the camera lens. That is sun clear. You can't see the objects clearly. So these are the different situations you have to deal with when you build or you develop the practical solution. So go to the other slide. So how to deal with varying illumination? Well, for indoor imaging, you might go with the image processing algorithms. There are plenty of image processing algorithms. So you do a pre-processing before you train a model, or you do an image segmentation, you pre-process the image. So like the histogram equalization, where you will equalize, like normalize the intensity level, so you can see the objects in the dark area quite improved. But the overexposure or the color washing is still a problem. So if something is overexposed, you just see it whitish, you don't know the true color. So it affects the rest of the programming. So in such situation, you are in the orchard. Now, one solution you can use is the artificial lights. So you will have a constant illumination, so there is no big variation, and you can use their algorithms. So if you want to go a cheap way, that you can use normal LED lights that you can buy from the market, and you can go do the imaging in the night for this orchard, or you can use high intensity xenon strobe lights or flashlights. So that throws the flash against the sunlight, so you can see the object on the image clearly, more clearly. So we have developed, so I'll take an example. We have developed a mobile app to get the size of the fruit. So you can see on the bottom left image, we have a board, the behind, so you don't want the background things, because if you want to segment the object, then you don't want the background, you want to remove the noise as much as possible. So that's why we have the backing board on the back of the fruit, and we take the image, and on the right bottom image, you can see the length and the width of the fruit displayed. On the corner, you can see the weight. You can find some relation to calculate the weight as well, just from the image, if you have enough data for calibration. So in this situation, if you went to the field and instead, like, you have a white background, so you like, say you get a paper, a printing paper, and you put a paper and you just take the image. So you think that's the white paper, and you take the image. Here in this area, you see the shadow. So if you have that white background and you take that fruit and you go for the segmentation, you can't segment that like this the fruit properly, because the shadow will also get into the fruit region, and then you will get maybe a bigger fruit, and when you calculate the dimensions, it will be wrong. So to reduce the shadow noise, what we did was we used the color space conversion. So normally we have the RGB image, and we can use a OpenCV or some other softwares to convert from one color space to other color space. So in many cases, the color space conversion will let you simplify your problem largely. So here we change it to LAB space, and in that LAB space, we can just discard the blue color. So when you change into LAB space, and here you can see the two peaks, the histogram of this image. So then, if they are well separated, you can use the dynamic thresholding method. So you don't need to specify any threshold values inside the program. You can use some of the dynamic thresholding methods that will look for the two peaks, and then you can segment. So you get a segmented, well segmented fruit on this side. You can see here. So that's after LAB space conversion and then the thresholding, and then you can draw a box around, calculate the area, or calculate the length, width, whatever dimension you want to. And if you look at this, you can see a yellow circle here. It's of a fixed diameter. I think it's a 2 millimeter radius, so 4 millimeter diameter. No, it's not 4 millimeter, 4 centimeters diameter. I think, I'm not sure, but it should be 4 centimeters. But you can have any. So this will work as a scale. So whenever you calculate the size, because the objects will appear bigger if it's close to camera, and if it's away from the camera, it starts looking smaller. So you don't know the exact size. So you need to know the distance from the camera to the object to calculate the exact size of the object. So we take that marker, the yellow marker here, as a scale. So we know how much is 4 centimeters looking on that image, and based on that we calculate this size. Scalability is what you have to think in practical life when you design solutions. Well, mobile apps, mobile phones, they have so many sensors you can utilize. That's a good thing. But will that scale up? So if you want to use this app, you can use it for like a small farm. You have a small farm with a couple of trees, you can go and do this. But if you want to develop a solution, a software for a big orchards, commercial orchards, you just don't ask them like, take this mobile phone, go and capture some trees, take the images. No, it's not possible. So you have to scale up. So you need more data. You need to cover many trees. So possible solutions is one to drive a vehicle, put the camera, start capturing the video, or fly the drones, or capture the satellite imagery. So it also depends on what application we're going to do. So satellite imagery is normally or usually capture and analyze for the vegetation index to find the health. In a big area, you want to find the health of your trees are healthy or not, and like that kind of things. But if your fruits are on the side of the trees, your satellite imagery will not capture them. So you need to do a side imaging, so you need to maybe drive a vehicle. Oh yes, so what we did here, this is how we did the nighttime imaging. So there's a light, LED light, and we have the computer up there, and we have the GPS, and then we have camera, so we keep driving, and then the computer will record the videos, and we analyze the videos later for fruit detection or flower detection. In the middle, you can see so how it looks like. If you do the nighttime imaging, you can see more clearly most of the fruits. So it's very easier for the model to train. So you don't need a complex, big deep learning models to train, because the image is already really good. There is less variation, so you can train small models, and that's really good. And it's going to be more accurate. On the right side, I don't know what's the context in other countries, but here in Australia, the farmers, they usually go in the night for spraying the trees. So in the front is the tractor, and it's connected to the sprayer on the back of the tractor. And this is our imaging rig. So the computer is inside here, inside the box. This is the camera. So there are 2 cameras facing 2 sides, and 2 LED lights, and this is a GPS receiver to capture the GPS location when you are capturing the images or the videos. So while the farmer is spraying, at the same time he can collect the data and then analyze later. So without wasting any time, he can get more information that's useful for him for farm management. So here is another way of estimating the fruit size using the machine vision. So in the last slide, I've shown you the mobile app. And this is like for scalability. So you are just taking the images of the trees, and then you want to sample the fruits for getting the size distribution across the orchard. So this one uses the depth camera. So depth camera can be a stereo camera, or it can be a time of flight camera like the Kinect camera or the real sense camera that's widely used in robotics. So on the left side image is of the mango of the tree. It's the RGB image. On the right side it's a depth. That's the heat map. So you can see the varying depth with the color. So first you do the detection on the mango here using your model. But you want to get the size of the mango that are really obvious and fully seen on the images. You don't want to go with the occluded, so you'll get a false reading if you just go with the occluded and that's hiding. You only see the small part, so it will disturb the accuracy of the fruit sizing. So what we have done here is we fit an ellipse. So we use OpenCV algorithms to fit an ellipse. So if an ellipse is perfectly fit on the fruit, you know that's the whole fruit. So then you look at the corresponding depth image here, and then you get the depth value. That means you will get the distance to that fruit. So once you know the distance and you have the image, the pixel area, you can calculate the size, the length, and the width. So for the machine vision deep learning, it's a supervised training. You have to prepare the data. So mostly you use the bounding box method. There are several other methods depending on the application. You can go with the pixel level segmentation, like the instance segmentation or semantic segmentation. But if you can do something easily with the bounding box, it takes less time than doing the pixel segmentation, and so it's easy. You just want the easy solution, isn't it? So you just go do the boxes like this, like this, like this. So and then there will be software. Don't worry about it. There will be software you can download, and whenever you do the box, and you can just label it as, you say M for mango, F for flower, and like so. So for each of the box, you have a label M, 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 and M, and that will write to a file, maybe XML file or a JSON file, any file. It will write the coordinates of each of the boxes. The coordinates of the boxes, the bounding boxes that you have drawn, and the label for it, whether it's a mango or it's a flower. And then while you send these images for training, it will first parse, look into that file, go and get the coordinates, and just get that portion out of the image and match the label. Okay, this is mango. I have to train it as a mango. Okay, go and grab another one. Oh, that's another fruit or something, and just go and train it as that label. So that's how you prepare the data, and then the model trains on that data. So it just takes that into the training, choose the data, and finally it predicts something, and it just checks over whether did I predict it that is a mango. It was a mango, but did I predict that as a mango? If not, I'll change the some values inside the model and try to make it correct every time. It's in a loop, so it takes a lot of time during training because it's always trying to learn something. So, and the other thing is you have to draw these boxes as tight as possible, because you don't want to train on the noise. So everything outside this fruit area is actually a background for the, so you don't want to have too much background. You just maybe have 10%, 15% background, and just rest should be your signal where you have their information. So just try to do it really tight, but not very tight. So because if you do it really tight, you might lose the shape feature. So it's like, you know, it's a curve here. So you have to, the machine learning should also know there's a curve, and then look at that color and the curve, and then I will determine that as a mango. It's not just the color I'll determine as a mango, because if it just looks for the color could be similar on the lips or the background. So yeah, that's not going to be good. Well, so we've trained a deep learning model, a convolution neural network, and then we send an image for detection of the fruits. On the right image is where you have the whole tree, the full tree image, and these boxes are where the model thinks they fit. And then the left image is where it's zoomed in version, where you see like more clearly these boxes. It's like where the model thinks the mango is, and I've labeled it as mango. Sorry, I've labeled it as EM, so it counts as EM. I think that's the EM the model is telling us, and that one is a confidence label. So the model, when it predicts something, it has got its confidence label. So the one is 100%. So this mango, he knows, or the model knows, I'm 100% sure. This one, the other one is 0.999, 99.9% sure. This one is a little bit unsure because you have seen some leaves there, so it's not quite sure, but it's pretty confident, but it's a little bit not as good as this one. So once you do this, you have the counts of the number of the boxes, and the number of boxes give you the frequency. So in the previous slide, that was only a case of a one class modeling. So you have only one class as a mango or a fruit. Now here, when you do the flower detection and classification, so you just don't not detect it's a flower, but you classify it into several stages. So you have three different stages of the flowering. So A is the very early stage of flowering, B is the middle stage, and C is the late stage of the flowering. So I was really interested to know like how much of my in my farm the flower has gone to a mature stage. Now it's going to bear some fruits. So I can get that information if I do this. But what I want to emphasize here is actually in the publications, people have 8 stages of a mango flowering. I try to do the modeling on the 8 stages, but what happens is when I go from one stage to the other stage, I had to do the labeling as I did. So I had to put the ground truth label. Okay, this box, I call it stage 7. This is stage 8. This is stage 6, and so on. But while doing that, you get confused. Did I do it 6 or 7? No, I put it 6 or 7. So if you do like that, your training data will be wrong, and then your model won't get trained properly. So that's why instead of 8, I have done here 3 stages, so you can visually tell the difference. Okay, that's early, that's mid, that's the latest stage. So you can label it correctly. So once you label it correctly, it's easier for the machine learning. It's easier for the models to get trained, and it's more accurate. So think on that way. On the right is the actual trees where you do the flower detection, several stages for different color bounding boxes for different stages. So the models we have used for flower and fruit detection is a deep learning model. So we have designed our own model that's based on YO framework. If you have known, that's a object detection framework. It's a really fast, and it's a one-shot class object detection model. So the convolutional neural networks have proven themselves to be very effective and successful for object detection and classification tasks, especially for image. And these deep learning models, they can, if you just label them, show them what the data is, they can learn themselves through the machine learning process. They will just learn what features they need to predict that data and the output correctly. And they have also proven to be very much, they have a good capacity of generalization. So with the generalization, I mean, like if I train on like this kind of lighting condition, and if I just take it to some other lighting, it still copes that environment, it still can detect something. Maybe it detects with lower confidence, but it still detects something. So that's why it has got more generalization capability. But if you do some thresholding kind of things, do the traditional methods, they can't cope this variation as much as the deep learning methods cope, because they are trained on large data set, and they can capture all the variations. That's all. So here's a little bit of a method comparison. On the left is where I've used the traditional machine learning. That's a support vector machine plus some color thresholding. And this segmented the flower pixels here. But you can see in this area, there's a little bit darker, and that's why this method is not detecting panicles or the flowers in this region, the crown of the tree. But in this one, we have used the deep learning on the right one, the right image, and you can see even this in the dark regions, you still can capture those. Here, the traditional method falsely identified the tree branches that have similar pixels, the tree leaves that have similar pixels as the flower pixels. But on the right, you can see the deep learning method is more robust. It just detects the flower panicles. So it's better. Okay, there's a lot of questions around deep learning models black box. No, they are not. They are not a black box. Because they are based on mathematics, and you can visualize, you can see what they are doing. They're not doing anything at random. Here, this image is like what I have done is I've trained a CNN deep learning CNN model to detect the to count the number of fruits. So in the training data, I have image. So this image has 20 fruits. The other image has 50 fruits. This has 100 fruits, and so on. And I put that in a training CNN regression model, and then it just does a convolution and takes into the model the image, and then it predicts on the count. But later I want to know whether the model is doing the right thing, whether it's looking on just the background and randomly predicting the numbers, or whether it is looking at actually the fruit regions to give me the fruit counts. I can visualize. So this is a visualization of the last layer in the convolutional neural network, just before you do the prediction. And you take in the input image, and then you do this heat map, and it shows, okay, the model is actually excited by these regions. So you are quite confident that the model has learned good things like what you wanted it to learn, because it's looking at the fruit region to detect to predict the number of fruits. So that's a gradient map actually. So you have the counts on the video. So you do the video and you started detecting the fruits, you have started detecting the flowers, you are counting them, but frame by frame for the same tree, you will have so many fruits. So you have to associate this fruit belongs to one tree. This fruit or this number of frames belongs to the other tree. So what can I do? So the one solution is, okay, because I know how to do the object detection, I can do some machine vision stuff. I'm happy I'll train the trunk detection. So you train a model to detect the tree trunks. So whenever in the video you run the algorithm, and whenever it sees the trunk, and when the trunk is centered in the video, in the image, it will capture that frame, or it will and save it as an image, and you can process it for the fruit detection or the flower detection, and then you can associate, okay, this tree has got that number of fruits. Here you can see there are 3 trunks being detected in one video frame. So you can utilize the distance between this trunk from the center trunk to these other trunks, and you can just go from the middle and segment that middle tree and just count the fruits. The other option is to use tracking. If you can't utilize this kind of technique, you have to go with the tracking, because you don't want to accumulate your counts in each frame. You want to know the exact count for one tree. So here is an example video. It's not of good quality because I was using my mobile phone to capture this from my desktop. but you can still see that's on a video, and the flowers, different stages of flowers are being detected. So on the left, you can see the trunk detection algorithm. So whenever it detects the trunk, it gives you a little pause because it's saving that frame for post-processing. So on the left is here is a tree trunk being detected. On the right is the flowers being detected. So then, yeah, that's all. So let's go to the next slide. So here in this slide, we're doing a fruit tracking. So you can see the frame number is increasing in 13, 14, but you can still see 36, 37 fruits. So whenever new fruits will appear, they get counted, but whatever has been detected is, you don't have to count it, because if you do a double counting, you will get more numbers. So you keep a track unless it disappears out of the frame. So anything coming in will be added, anything going, and keep the track once it's detected, and then you get to get a count of these total number of fruits on the tree. We have some advantage with this tracking method, because you can see the fruits in a different angle. They are being tracked, and then so many fruits will reappear, like they can appear, and you can count multiple, now you can count more accurately the number of fruits. Instead of, if you have just one image, you will have only that view, and whatever is seen in that view, you will just get that. But with this, you're just moving, your view angle is changing, and so you can get more fruits. And yep. So you have the counts, you have the fruit counts, you have the flower counts, different stages classified. Then you also have the GPS points. So you can plot that on the Google Maps like this. So this is one block of the mango farm. So, and then you can just do some color dots, like the red one is here. You can have some thresholds. So if it's more than 25% flowering, go with the red and green and different colors. You can have different dates. So you can just do some software development, the web development to display this thing. So if you have that, that's not just the dots. You can see some patterns. So in this area, the red areas, you have, okay, I'm more advanced flowering, there are more number of flowers. This area has less flowers, so I need to spray this area, I need to spray this area, or this area is going to get more fruits, early fruits, because they are already advanced there. And then later, so that will help you doing a precision spraying. So if some certain area doesn't have any flower, don't need to spray. So you know the location where you have the flowers, more flowers to the less flowers. Early harvest is if your flowering is in the early, like now matured in the stage, so they will produce fruit early. So you can send the people to pick on that block, because there will be several blocks in the big farms. So, and then for fruit yield estimation, so you know the count, you know the size, so you know, okay, there are this number of fruits coming this season from my farm. So you can talk to the market agents and say, okay, I can deliver this number of fruits. So that helps them to do some market planning, and then they can arrange for the trucks, they can arrange for the storage, the cold store, they can arrange for the fruit picking laborers, and so many things. So it's like it provides them as a decision support system. So finally, time to pick fruits. So now you have the machine vision solution. You can detect the fruits, and you can use the depth cameras to get the distance to individual fruit. So what else? You know the location and you know where it is. It's time for automated harvesting. So you can use the robotic arms to go to that location, grab a fruit, and collect those fruit for you. Why I'm putting this one here is, whenever you say a picking robot, you will just normally visualize this arm. It's a standard industrial arm, so they are more suitable in the industrial, like where you have to move the parts from one place to the specified other place. They have 6 degrees of the freedom, so they can 6 or 7 depends. They can do that, but Do you think that's scalable? Now I can't. I can. They are very useful in the like where the plants are small. If you go into the greenhouse environment and like they have the strawberry plantation, you can take this. You can pick the strawberry autonomously and then sort them out. But if you take this out in the mango farm where like the trees are 4 meters and 4 meters wide, 4 meters tall, and you have this arm and it can't reach that far, and it takes a lot of time. Like it has to like this maneuver, and then it has to go and grab the fruit. It takes so many it takes a longer time to even pick one fruit, so these are not suitable for the big trees. They can't do. So there's again the scalability things. I just wanted you to emphasize on that. On the right side is our robot. So it's very tall. It's very tall. It has got several arms. At the moment, there are 10 arms. So they are using the linear actuator, so it can go straight 3 meters inside the canopy. So they can go like this, very quick. 1 second go, grab the fruit, come back in 1 second. So you have the area of like 10, 12. In the new robot, we have 16 arms, and the whole platform will just keep lifting up and up. So it finishes that line. So it sends out all the arms, grab the fruit, and goes to ender level, and grab the fruit, goes to ender level. So it scans from the bottom to the top of the tree and picks all the fruit in very less time. So this one is, see how tall it is. This is our robot. And it was in the initial stage where we were just operating one arm to grab the fruit. So we were in the trial stage at that time, but we have already modified a lot of things with this robot. So it's now lifting up and to go to the next level, and shoots out, twist the fruit, come back. So we have so many other robots available. There are like apple picking robots, some citrus picking robots in the US and a few other countries. But mango is something different. It's more challenging because of the tree structure. It's very unstructured canopy. The other thing is you have to twist the mango. You can't just pull it straight away, because when you break the stem, when you break the stem of the fruit, there will be sap sap is coming out. It can burn your skin, and then if the sap is on the flesh of the skin of the fruit, it's not marketable. So you will get less value. So within 3 to 4 seconds, you have to put it deep in a water with the chemical, so it just washes that sap. So that's why we have the water trough on that robot here. So it's just dropping on that water. So it's quite challenging. You have to twist and do several things. So where are we at the present? We've seen the machine vision and AI and the deep learning. They are finding several applications in the agriculture domain, from quality assurance, like you have the mobile apps to detect the defect on the fruits, do a quality testing or whatsoever, and you can also estimate the quantity. In the industrial settings, you have a big industries where you sort out the fruits based on their like defects. You use the cameras in the industry, fixed cameras, industrial cameras, and they have got a very good environment there. So it's already matured there. It's already mature, like, and in the greenhouse environment, it's already matured. But it's now time to take those out to the big farms, unstructured environment where you have the different kind of factors, like extreme environmental factors, and it's a challenge. So what's available to us these days? So there are more and more industrial grade computers available to be used on extreme farm environments, so they can tolerate high level of and low level of temperature and pressures, and that like the jerk, like you are driving and there will be so many bumps and jerks in the farm, and it has to tolerate that as well. So physically and computationally, they also can come with the GPU. So if you have the graphical processing unit, GPU ground, you can process the images in real time if you want, and that's going to be really good if they want it to. If internet is available, cloud computing is another thing. So you don't need to physically buy a computer, you can just pay some money. You can just put your algorithm in the AWS cloud or Amazon cloud or wherever, and you can upload your images to that server, and it get processed over, and then you get the output. But internet, you need the internet. But if it's a big farm and you have so big videos, it's very difficult. If your internet is slow, you will have to wait for a couple of days to upload the data. So in that case, you will probably think of processing on the field. So you will have to buy industrial computers that are really small form factors, and they have got a good CPU. And these days there are several gateways, and that can handle hundreds and hundreds of the sensors. You can buy it in the market, and you can put the temperature sensors, pressure sensors around your field in the orchard, and then it is streaming out the data, and you have the internet. You can go and you can see the live data, live plot, and you can utilize that live data, the temperature data, whatever data it is. You can do some sort of machine learning on that one. You can do some sort of time series prediction on that one. So whenever it's from flower to the fruiting, everything depends on the temperature. So daily minimum and maximum temperature affects the number of days it takes to transform from fruit to the from flower to the fruit and to the maturity. So we can take the current readings of the temperature. We can compare with the historical data of 10 years data from the Department of Meteorology or whatever weather bureau, and you can do some sort of machine learning. You can predict when you can harvest your fruit, when it's going to be ready. You have that scope in there. And these days you have so many public data set available to train and test your algorithms. You have so many already trained deep learning models. You can do a transfer learning, and you can train on your very small set of images. So you can utilize the transfer learning here. So from where are we going now? So the machine vision and AI are already being accepted as the future technology in agriculture domain. You can see driverless autonomous car, not autonomous cars, autonomous vehicles in the farm, like in the border, like there will be very big area. It's going there, and it's just detecting the weeds and killing the weeds. It's spraying and doing so many other activities. Commercial farms, they have started changing the structure of their farm, so they can allow the vehicles to turn around, go in each row of the orchard. They have also changed the structure of the tree. So they will make, nowadays they are making trees very small and wide open, like a 2D structure in the trellises. So it's easier for the machine vision to see the fruits, and it's easier for the robots to go and pick the fruits. So people have already started, and we can see those in apple. Like nowadays, the apple, they are grown in 2D spindles or the trellises. Mango plants, they are doing trial to reduce the size of the tree, and by cutting and pruning, and then like trying to do it in the trellises like 2D. So they will do a high density plantation. You'll have so many trees, but it's small trees. So your productivity won't change because you have many trees. You can grow many trees. They're like touching each other, very less spacing, but open trees, so they can get the sunlight, and then the fruits can be very good, and it will help the robots to pick them or do the imaging. So good visibility is more accurate machine vision estimate, easier robot picking. So this is an example of a mango plants going in the trellises. So you can see these the wires there, the strings. So they will just like try to bend the branches and just try to crawl on that string. Try to crawl on that string. So they looks like the 2D. So you can see almost all the fruits. So that's what we want in the machine vision, isn't it? We want to see all this, and we want to count this, and we want to be more accurate on the prediction, and we want to pick it really quick, easily, no obstacles. So the takeaway notes: even though you are expert in the machine vision software programming whatsoever, But data acquisition is the very important step in machine vision or computer vision. If you go like, if you don't have a good data, if you don't have a good signal, you can't extract the good information if it's too much noisy. So you can do some sort of pre-processing, but if you don't have a good data, now it's not going to work properly. So you have to be really very careful in doing the data acquisition. And choice of the machine vision hardware and the computational resource is specific to application type. So either you want to do it just an indoor application, or you want to have a big customer, you want to do these, deliver the software or your product to a big company, industrial company, or it's big farms or whatsoever. That decides what kind of how you develop your software or the product. So what type of cameras you want to choose, and what kind of machines, what's the ground, whether you can just do it with the mobile phones or Raspberry Pis or small electronics, or you just have to do with the GPU and the cloud storage and something else. It's totally dependent on what outcome you want and what's the scenario you are going to do, what's the problem. And you will always need to think about the scalability of your product beforehand you develop something. So later you don't get stuck in it, be a bottleneck. I've spent so much time doing this. Now the customer is asking, can this be utilized or used with, shared with so many people or something? Then so no, I didn't have that thing in my software. So you have to think beforehand. You develop something, you think, okay, where it's going in the future, how much you can scale up, so to what level. So that's all. Thank you. So much have been done and much to do. So there's so much have been done in the agriculture field. We're using getting the technology from other fields that's already been matured and try to implement. There are so many other spaces inside this field where you can still get into and do your job, do some solve some problems. You can contact me. That's my name and that's my email address. Now I'll open up for the question, but yeah,